Mineral arts dates back to early human civilization. Mineral science begins with Renaissance or Age of Reason. In 1700s started measurements of crystal geometry and symmetry. Early 1800s precise measurements of crystal symmetry heralded the field of crystallography. Analytical chemistry leads to chemical classification of minerals. Late 1800s creation of polarizing microscope opened the field of petrography and the study of optical properties of minerals. Early 1900s X-ray diffraction measurements allowed for precise measurement of internal symmetry and structure of minerals. 1960 onwards development of the electron microprobe allowed for accurate in situ analysis of mineral chemistry. 1970 heralded the development of transmission electron microscope which helped in visualization of atomic structure and symmetry. In 1980, ion microprobe advent allowed for the study of isotopic composition of minerals. Mineral is a naturally occurring inorganic substance having definite chemical composition and regular internal atomic structure. The chemical composition of the mineral is fixed or varies only within well defined limits. Mineral is naturally occurring non-synthetic. This eliminates all unnatural man-made substances like plastic and synthetic compounds. Mineral is a solid. This eliminates gases and liquids. It has ordered atomic arrangement, means atoms are arranged in some geometric pattern. This eliminates inhomogeneous solids such as glass. The ordered atomic arrangement is reflected in the crystal form and cleavage of the mineral. Example, the rhombs of calcite. Chemical composition which is fixed or which varies within well defined limits. All minerals are characterized by a chemical formula. Some minerals have chemical substitutions in which ions of similar size and charge freely substitute for each other, such as the plagioclase series. Among the infinite variety of the mineral kingdom, which constitutes more than 4,000 minerals, there are certain substances which stand apart from all others by the possession of exceptional characters, attracting the attention of persons endowed with taste and refinement. The question then arises onto what are the essential qualities for the mineral to be called a gemstone. The basic qualities that make a gemstone and gem materials suitable for use in jewelry are beauty, rarity and durability. A gemstone is a mineral or an aggregate of a mineral which due to one or more optical properties can be rendered sufficiently beautiful through cutting and polishing, so as to be used in jewelry or other decorative purposes. The cut and polished final product produced from the uncut gemstone is called gem. Since the middle of the 19th century, minerals have been classified on the basis of their chemical composition. Under this scheme, they are divided into classes according to their dominant anion or anionic group. Example, halides, oxides and sulfides. Several reasons justify use of this criterion as the distinguishing factor at the highest level of mineral classification. First, the similarities in properties of minerals with identical anionic groups are generally more pronounced than those with the same dominant cation. The broadest divisions of the classification used in the present discussion are: number 1, native elements, sulfides, sulfosalts, oxides and hydroxides, halides, carbonates, nitrates, borates, sulfates, phosphates and silicates. Once minerals have been grouped by chemical composition, they can be further separated into groups on the basis of internal structure. Now, let us discuss this classification one by one. Silicates, minerals whose crystalline structure contains the SiO4 tetrahedra. The silica tetrahedra is the basic building blocks of all silicate minerals. Silica and oxygen make up about 74% of the Earth's crust. Silica with a charge of +4 bonds with 4 oxygen with a charge of -2, such that there is a residual -4 charge. Other cations like calcium, sodium, magnesium and iron either link the tetrahedra together or are incorporated in the tetrahedral structure, determining the mineral form. As these silica tetrahedra are linked together, the ratio of the silica to oxygen changes. Example, single tetrahedra 1:4, single chain 1:3, double chain 4:11, sheets 2:5, three-dimensional frameworks 1:2. Ferromagnesian silicates. Silicates with iron and or magnesium in their structure are ferromagnesium silicates. Most ferromagnesian minerals are dark colored and more dense than the non-ferromagnesian silicates. Non-ferromagnesian silicates include substantial Fe and Mg in their crystalline structure. These are generally lighter colored than the ferromagnesian silicates. Next is carbonates. Carbonate minerals which contain the carbonate, that is CO3 to the power -2 anion complex are carbonates. Calcite, calcium carbonate, which occurs as thick masses of limestone, chalk and marble. It is relatively soft with a hardness of 3 in Mohs scale of hardness, has perfect rhombohedral cleavage of 75 degrees and reacts with hydrochloric acid. When it reacts with hydrochloric acid, it liberates carbon dioxide, water, chlorine and calcium. Calcite is commonly precipitated from concentrated solutions or extracted from seawater by marine organisms, that is coral reefs and muds. Sulfides, minerals which contain the sulfur anion are sulfides. Sulfides include arsenites and tellurides. Here As replaces sulfur and acts as an anion. Sulfur salts contain approximately 100 species. In these minerals with As and Sp play a role more akin to metals than anions. Many important silver minerals are sulfur salts. Galena is a lead sulfide which has a metallic luster, perfect cubic cleavage and a high specific gravity, that is 7.5. It is the most important source of lead. Pyrite, it is a sulfide of iron which is a yellow metallic mineral which has a hardness of 6 to 6.5 and lacks cleavage. It has a greenish black streak. It is an important source of sulfur. Oxides, minerals which contain oxygen ions are oxides. Simple and multiple where oxygen combines with one or more metals, that is cations, and hydroxides with OH group and H2O molecules. Hematite, it is oxide of iron which is commonly dark red to steel blue black. It gives a deep red streak, lacks cleavage and has a moderately high specific gravity. It varies from 5 to 6.5. Hematite is mined for its iron content. Limonite, it is a hydroxide of iron, a yellowish brown colored mineral which usually forms by the weathering of iron minerals. It is characterized by a yellow streak, absence of cleavage and a dull rusted metallic texture. It is also mined for iron. Next is halides, minerals which contain chlorine, fluorine or any of the other halogen elements as anions or halides. Halite, it is a sodium chloride characterized by cubic cleavage, clear or transparent in nature, and has salty taste and shows resinous luster. It forms by the precipitation from seawater. Fluorite is calcium fluoride, which has good cleavage in 4 directions, variable color, hardness of 4 and a specific gravity of 3. Next is native elements, with the exception of gases, make up about 20 minerals. These are further divided into metals, semi-metals and non-metals. Examples of the metals are gold, silver, copper, platinum, palladium and iron, and of the semi-metals are As, Sb, Bi, Se and Te, and of the non-metals are sulfur and carbon. Next is nitrates. In nitrates, only 7 known minerals are there, and its composition is NO3 with a charge of -1. Next is borates. Borates, they have a composition of BO3 with a charge of -3, can form polymers. About 100 known minerals are there in borates. Phosphates, the composition of phosphates is PO4 with a charge of -3, are usually hydrous as well. Sulfates can be hydrous or anhydrous. Tungstates include the minerals like scheelite and wolframite, which are both ore minerals for wolfram. Economic minerals, minerals with a commercial value or economic minerals. Ore is a mineral or aggregate of minerals that is economically mineable, and it varies according to the demand. Precious metals, these include native metals like gold, silver and copper that occur in pure deposits, and also metal bearing minerals such as galena and hematite, limonite, magnetite. Many of these are strategic minerals, minerals that are critical to our national defense. We currently import more than 50% of the top 13 strategic minerals such as cobaltite and chromite. Non-metallic ores, these include all non-metallic minerals that are used most commonly for industrial or constructional purposes. Examples include halite in food preparation, kaolinite in ceramics, calcite in concrete and fertilizer, gypsum in wallboard, quartz in glass and concrete, and fluorite in iron smelting. Gemstones, precious or semi-precious stones that are cut and polished for ornamental purposes. They are characterized by high hardness, unusual color, brilliant luster and rare occurrence. Most minerals contain impurities, and several also display ionic substitution. There are other minerals which have identical chemical composition but different crystalline structure due to the conditions under which they crystallized. Impurities. Most minerals have non-structural ions trapped or included in the atomic structure during growth of the structure. Ionic substitution. Variations in composition resulting from a systematic substitution of ions. There are several minerals which display solid solution, that is, solids which act like solutions during crystallization and melting. The olivine group, which contains phosphorite, the composition of this phosphorite is Mg2SiO4, and it ranges to phyolite, the composition of which is Fe2SiO4, is a good example of solid solution. Both Mg+2 and Fe+2 have the same charge, that is +2, and about the same ionic size, so that either can fit into the olivine crystalline structure. Next is coupled ion substitution. The plagioclase series is a best example of a solid solution for coupled ion substitution, which varies in composition from NaAlSi3O8 to CaAl2Si 2O8. The ions do not have the same charge, but are able to substitute for one another when coupled with another ion. Within the plagioclase crystal structure, Ca plus 2 and Al plus 3 with a combined charge of plus 5 substitute for Na plus 1 and Si plus 4, which also have a combined charge of plus 5. Next is polymorphs. Minerals which have the identical chemical composition but different internal structure. The best examples are the carbon polymorphs, diamond and graphite, which are both composed of pure carbon but have substantial difference in their atomic packing and bonding. Next is common rock forming minerals. There are over 3,500 known minerals with several new ones described each year. However, only a small number of these are abundant. Minerals are grouped according to the anion or anion complex that they contain. Example, silicates SiO4 with a charge of -4, carbonates CO3 with a charge of -2, sulfides, oxides with a charge of -2 and halides, that is chlorine with a charge of -1 or fluorine with a charge of -2. The minerals in each group often display similar properties and are commonly found together due to their similar chemical composition. Mineral, which is a naturally occurring inorganic substance having definite chemical composition and ordered internal atomic structure, can be identified with the help of physical, optical and chemical properties. The physical properties of minerals are used by mineralogists to help determine the identity of a specimen. Some of the tests can be performed easily in the field, while others require laboratory equipment. However, there exists a whole lot of physical properties that are helpful in diagnosis of a mineral. So, in the foregoing talk, the physical properties of minerals are discussed. Minerals have distinguishing physical properties that in most cases can be used to determine the identity of the mineral. The physical characteristics of minerals include traits which are used to identify and describe mineral species. These traits include color, streak, luster, density, hardness, cleavage, fracture, tenacity and crystal habit. Each mineral is characterized by a set of physical properties that assist in its identification. External shape or form or habit, weak planes, hardness and tenacity, specific gravity, color, diaphanity and luster are some of the important physical properties of the minerals. Color, however, is variable and is dependent on impurity and other factors. Diaphanity is an important property which qualifies a mineral to be called as a gemstone. Unusual properties like incandescence and catayency are characteristic of some of minerals which elevate them to the level of gemstone. Properties like luminescence and those based on magnetism and electricity help in distinguishing certain stones or minerals. A few minerals have characteristic odor, taste and affinity to water and grease. Synthetic minerals have physical properties analog to their natural counterparts. Man-made minerals that are not represented in nature also have their own distinct physical properties. Minerals are characterized by certain definite physical properties, chemical composition, optical properties and internal molecular structure, and hence the study of minerals is made under different heads like physical mineralogy, chemical mineralogy, optical mineralogy and X-ray mineralogy. The properties such as pleochroism, extinction and extinction angle, twinning and accessories of transmitted light microscope are all dealt under the head optical mineralogy. Optical mineralogy deals with the study of optical properties of minerals in thin sections and grains under a special type of microscope called petrological microscope. There are different optical properties which aid in the identification of minerals. The most prominent are color, shape, cleavage, relief, alteration, exsolution, pleochroism, interference color, extinction and extinction angle, twinning, refractive index, twinkling, birefringence, etc. are important for the identification of minerals individually and also when they are the constituent of the rock. Chemically, minerals are identified with the help of their composition. The composition of minerals nowadays can be determined with the help of sophisticated analytical techniques like X-ray diffraction, electron probe microanalyzer, atomic absorption spectrophotometer, inductively coupled plasma spectrophotometer, etc. Minerals are a critical part of our everyday life. They are used in the construction of our buildings, homes, roads and machines. They are used to fertilize our crops, produce energy for our homes, add flavor to our foods and even make many of our medicines. Gem quality minerals are used in jewelry and ornaments making. As civilizations progressed from the Stone Age to the present, humans learned new and different ways to use minerals and earth materials to better their living conditions. Rocks are aggregates of one or more minerals. Therefore, mineral identification is also a crucial part of the classification of the rocks. Minerals are part of our civilization in the past and also at present. Understanding of the various aspects of mineral kingdom is very important for the progress of our society. Minerals can be identified with the help of physical, optical and chemical properties. The physical properties like color, habit, cleavage, fracture, hardness, specific gravity, etc. and optical properties such as crystal habit, color, relief, pleochroism, refractive index, interference color, twinning, extinction, twinkling, etc. not only helps to identify the minerals, but also to distinguish them from other minerals including the synthesized counterparts. The petrological microscope is an unavoidable tool for the identification of minerals and minerals present in rocks for the properties depending on light. The physical and optical properties mentioned not only serves to identify the minerals, but also helps in distinguishing the minerals showing the identical optical properties. Thus, mineral kingdom is an important branch to understand the importance of minerals.